Okay, so we're going to go over the problem 1 assignment. The assignment was to use fourfold cross-validation to identify the best hyperparameters. And these are the following hyperparameters we were intended to use. We use the IMD data set, which is one hot encoded. And here are all the imports that are used from TensorFlow, Karis, scikit-learn, and then all the regulars, NumPy, Pandas, Seaborn, Matplotlib, itertools. Here we are bringing the data in with Pandas read CSV method, and then so the data has been pre-processed already, so it's already been split into training data, testing data, and then the labeled data, and then the labeled testing data. And here I've just gone ahead and converted it to a NumPy array so that it can be tensor compliant. And then these are steps that we can skip. Here's the parameter grid. We've defined in a dictionary the parameters for the layers, the number of nodes in the layers, the learning rates, and the number of features. We combine those into 18 different combinations, and those also represent the 18 models that we're going to try to teach. And then here we've got our first method defined. This is the build neural net model method, and we're using Karis's sequential class to create sequential neural nets so that the one layer travels to the next layer, which travels to the next layer, which finally arrives at the output layer. And we're going to use the add method to add each layer independently, and then we give it the number of nodes. We're defining it as dense so that they're all fully connected with the next layer of nodes. And the hidden layer activation function is the ReLU function, which is a spin-off of gradient descent for the learning rate. And then we're going to add finally the last layer, the output layer, and the activation function used for that is the sigmoid function, which turns the output into a range from 0 to 1, and 1 represents a positive review and 0 represents a negative review. Then we've got the build combo models. So another note about this function here, the build in models, is that it is also responsible for the input layer, and only the input layer needs to know the initial shape of a single sample. So it would be a one-dimensional NumPy array of 10,000 features or 1,000 features, depending on our parameters that are used, and by nothing. And so it doesn't have another dimension. And that's what the input layer needs to know. Okay, so now coming down to the build combo models, it's going to take in our parameter combo that we created with our parameter grid, and it's going to take in the loss function that we want to use, which in this case is binary cross entropy. And so the parameter combos are the 18 combos and it's going to run those through and build the models using our function that we defined up here, and it's going to pass in the parameters based on the parameters that are from the parameter grid. And this is our compile, our Karis compile method, and from our model object. And here we specify the learning rate, and we pass that to the RMS prop. Oh, I misspoke earlier. So this is the spin-off of the gradient descent and affects the learning rate. I'm sorry, I got turned around here. The ReLU activation function for the hidden layers is not responsible for that. It is responsible for sending the output to the next layer that's used as the input for the next layer. Okay, so this is used to optimize and adjust the learning rate. Okay, so then we've got our binary accuracy for the metrics, and then we're going to create a list here of the model name, the model, and the feature size that we will use later. Okay, so moving on to run k-split validation, we're going to pass in our X training data, our labels, our models, the number of epochs we're going to use, our batch size, and the fact that I want to get the top and the top three and the bottom three of the models that it produces. So we're going to use stratified k-fold for our 4 splits, and the stratified part of the k-fold means that it takes the original so it takes the original ratio of the data, so the original data, in this case, the IMDb data set, has 50% that are negative reviews and 50% that are positive reviews. So when it takes so the data is split into 25,000 and 25,000. 25,000 are for the training data and 25,000 are for the test data. And then it takes the 25,000 of the training data and it splits that into 4 equal chunks. And then it takes each of those 4 equal chunks and evenly splits it, I believe, into validation and training data. It might not evenly split it. It might have a splitting ratio that it uses. And then, but it makes sure that the ratio of negative to positive reviews in both the training, the training and the validation are the same ratios as the original data, which is a 50-50 split. Okay, so now we're going to say shuffle is true to make sure that it's shuffling the data and it's not repeating itself. And we just picked the Hitchhiker's Guide to the Galaxy reference random state, and then we've got our dummy performers and our bottom performers, our dummy top performers and our dummy bottom performers set up at first, so it has something to compare to and say, okay, this is lower than, okay, this is higher than this amount, which, any number is going to be higher than negative infinity and any number is going to be lower than positive infinity, so that's how we set it up at first. Okay, so we've got our model histories list instantiated here, and then we're going to go through our model name. Okay, so we've got our list of model histories set up here, and then we've got a list of fold histories set up here. So from our, what happened? This is strange. Okay, so weird. Okay, so we've got our models that we passed in, and from that we're going to, remember this is where we were adding this up here. We're going to take out, we're going to go cycle through the model name, the model, and the feature size to separate those pieces. And here's just a print statement to let us know what's being evaluated when, so we can kind of see where we are. And this is where we're going to actually split the data using our stratified k-fold method here, and we're going to have a fold, and we're going to have a training index and a validation index. So these are going to be, it takes in the feature size, and it says we're going to slice that up to this feature size. So up to 10,000, up to 1,000. And we're going to say that that's the size of that chunk. And then we're going to split that chunk into 4 folds. And then we're going to do to it what I explained earlier. And then we're going to do that same thing to the Y train. So this is per model, that's per 18 models that are passed in. Each of them is going to go through this split. And then we're going to assign so it's saying for each of those, we're going to make sure that we assign the X train fold and the X val fold to those particular splitted areas. And actually this is not right. Okay, so this is the corrected version of this. I'm not sure why I had that in there. That was a mistake. Okay, so then so basically this is going to be split based on its feature size, right? So the training labels don't have features, they just have results. So that doesn't need to have any kind of split. That's why down here we're not doing anything with that. Okay, so now we're going to run our fold history. We're going to set our fold history equal to model.fit. Model.fit is what's going to be used to actually do all of the things that we want it to do. So model.fit handles the forward pass, the weighted sum, the loss calculation, which in this case is binary cross entropy, gradient descent, which computes the gradients of the loss for each weight and bias, which are partial derivatives using backpropagation, and it also updates the weights and biases using the chosen learning rate optimizer. For example, in this code, it's the RMS prop by applying the computed gradients. Okay, and then we're going to add that to the fold histories so that we can aggregate those. And we're going to aggregate them here. And we're going to use the mean to take the mean of the last index. Okay, so we're going to average all of the values in the NumPy array for the fold histories. And then we're going to take the last value of the binary, the validation binary accuracy, and use that to base our top performers. And then we're going to do the same thing to get our bottom performers in the lowest average. And then for finally, we're just going to put those together and we're going to send them on their way. Okay. That's something I didn't use. Okay. So then we're going to, I should just, okay. So then we're going to, actually run these, and pass in all of our parameters. We already made our parameter combo earlier, so we can just pass that in there. And then unfortunately, I don't have this up from the previous run, but well, I can run it real quick. Well, let's see. Okay, let's just do it. Okay, that'll take a second. So we used 20 epochs, a batch size of 500, and then it has a printout line, and these are the values that are printed out. Okay, so then we made a model histories dictionary, and we used that to use to pass to our plots, and then we could sort of manipulate those. Well, I guess I use my models here to create another dictionary, and let's see, and then we created these, which are the testing results for all of the models on the test data. So the 25,000 that was designated for test data. So completely unseen data. And I tried just looking for patterns. I sorted by number of layers, sorted by learning rate, by rate. So like all the 0.0005 and 3 and 1 are all together. And then this is learning rate by layers. So, like 1 layer, this rate, 1 layer, this rate, 1 layer, this rate, etc. And then the loss scores. Sorted by, sorry. And then this is the sorted by number of features. This goes a little higher than this, but it made it harder to read everything else, so I lowered it. I think these were 1.5 and 1.6, whichever one. Okay, let's see if we got our printout up here. Still on cell number 1. Well, alright. Let's go on. So now we're going to problem number 2. The only difference is that this is a single a single label multi-class classification problem. And we've got 46 mutually exclusive categories. One hot encoding is still used. Same here, same here. The only differences are going to be that we needed to use 12 different hyperparameters, and I'm assuming that's not 12 different categories of hyperparameters, but 12 altogether. So creating, I think, 64 different models. These are all the models that it based on all the different combinations. And then the differences are going to be that on the outer activation we need to use softmax instead of sigmoid. And then we're going to use, our metric is going to be categorical accuracy with the compile function. And in our folds, it's going to be validation categorical accuracy that we're going to base our top performers by. Here I still have it. This is the printout for what it looks like while it's running, and we can get rid of that. Okay, and this is just, and here's the, once again, we're going to plot the results. We've got our validation scores here with our, how much time do I have? Okay, so we've got our training accuracy, our validation accuracy. As you can see, these are fairly straight lines across here. So as the training data kind of arcs up and approaches 0.96, the validation data plateaus at 0.90. And that kind of does that trend for all three of these. The interesting thing is that they all use Kohler-Liebler divergence, and all of the lowest models, the bottom models, used categorical cross entropy. So these are the, I put in these extra cells just because it looked better and I didn't want to change things around from where I had it. So these are the loss scores, and these are the top models and the bottom models. So the top models sort of follow a similar trend as the accuracy scores, and these are not doing very well. Their loss is very high, and as you can see, their accuracy doesn't get above 0.46, 0.42, just above 0.35, and the validation data follows that training data pretty closely. These are 500 features, so basically it's inductive logic instead of deductive logic, and it's making inferences that, or categorical assumptions that are not really valid in creating good predictions. So I know a few people who do that too, and so their scores are mirrored in the validation scores, just as they are in the training scores, because they're still using the same logic on the validation that's producing the same incorrect results. Okay. So I think I've gone over on time, so I don't know if I can even talk about anything else. Thank you. Bye bye.